All right, happy Tuesday. We are in week 6. We're in our second to last chapter, and all of these Zoom meetings from here on out are going to be a lot shorter. As I said earlier in the term, I front loaded the term with most of the material, with most of the content, so that you would, number one, have a lot of math to work on your final project and have time to work on your final project. I intentionally made the lessons shorter and less material covered and less assignments, fewer assignments, the end of the term, so that you'll have time to work on your final project. So I would not expect the Zoom meetings from here on out to go longer than an hour. It's possible they could. It's always possible, especially if you have questions, but they're going to be fairly short because, as I said, I want you to be able to work on that, get that final project working on. Figured giving you extra time after the Zoom meeting, you can allot for yourself, hey, I'm going to spend a half hour on my final project or 45 minutes, whatever, or jump straight into the homework and then put some final project time in, because I don't want you to wait until the very last second. Obviously, this Thursday is the date for the data. So your data is due. You do not have to do any kind of analysis on it. All I'm looking for is for you to have your data, your raw data, and just put it in Excel, just the raw data. And then there are two different prompts that you have to respond to, and you can type those directly into Excel. Even if it like bleeds into other cells or doesn't look super fancy, if you just type it into one cell, I can still see it. I might have to click on it to see the whole thing, but I can still see it. So it doesn't have to be fancy. The purpose of having the project proposal and then the data submission is so that people aren't just waiting till that last minute. I want to make sure that you're working on it as we go. So that is due Thursday. Today we're going to work on section 9.1. So what we do today is going to look a little bit familiar to what you've seen out in the wild. What you see, I mean, we just had a presidential election in November, and you would see things like this particular candidate has 38% of the vote plus or minus 3%. That's a margin of error. We're going to learn how to calculate a margin of error. We're going to learn how to construct what's called a confidence interval, which will give you a range of values that are likely to be true. And we're going to talk about how do I find the correct sample size in order to get the margin of error that I'm looking for. So that's what we're doing today. Some of the concepts we're doing today will rely on what we learned in section 8.2. So some of the tests we did and the standard error slash new standard deviation. So this ties in with 8.2. All right. So we're going to obtain a point estimate for the population proportion. We already did that. That's the p hat that we found last week. We're going to be using that p hat again. We're going to be constructing and interpreting a confidence interval, and we're working with proportions today. And then we're going to determine the sample size. That is our lesson for today. And normally this kind of gives you an idea of the size of our the length of our class. Normally, I have 40 to 45 slides for a class. We only have 26 today, so we should be doing pretty good. All right. As I stated last week, a point estimate, you just take the number of successes or the number of the individuals that have a specific characteristic and you divide it by whatever our sample size is. That gives us our p hat. That hat on the p, we use a hat on a symbol whenever it is an estimate. So a p hat is an estimate because if we don't know the actual population proportion, we will use our sample for an estimate, and we'll call it p hat to indicate that this isn't the population proportion. This is a sample proportion. So Quinnipiac poll asked 1,783 registered voters if they favor or oppose the death penalty. 1,123 were in favor. So we're just going to get our point estimate. This should be familiar. Let me get my pen out. and you just divide it. So our p hat here is 0 point about 63%. So about 63% of the people that they polled were in favor of the death penalty when for people convicted of murder. Hopefully, p hat isn't anything unusual. You remember doing that last week, and we can just move on. All right, here's our vocabulary. So using our point estimate, because we just took a sample, we have an estimated value. Because our value is an estimate, we need to based on our sample size and information that we have, we use that to determine what is the range of values or the interval numbers that we are likely to find the actual population proportion. So for example, back here, we say 63% of voters are said they favor the death penalty. So 63% was our samples based on our sample. The population proportion's probably not actually 63%. So we need to find an interval of values. So it's possible it's like between 60 and 66% is the actual population proportion. So the confidence interval is that interval of values. So like between these two values, we expect to find the actual population proportion. That's what a confidence interval is. So our level of confidence. So if you want to be, you could be 99% confident that it's between 60 and 66. You might be 85% confident it's between 58 and 68. So depending on how confident you want to be or how accurate you want your sample proportion to be, or how accurate your interval to be, we pick a level of confidence. I'm always going to give you that level of confidence. You don't have to pick one yourself. However, if you are doing it with your final project, if you decide to construct a confidence interval for your final project, then you would have to choose your own. But I'm going to give it to you for all your homework and whatnot. So the way that we find that level of confidence, actually, I mean, I will tell you what it is. Ouch, sorry, my cat just bit me. So the level of confidence along with our sample size help us to determine that margin of error. It's going to help work out a lot more in your head once we actually have numbers that we're working with. All right. So this might be, this is the way that we interpret our confidence interval or our confidence level. So if I have a 95% confidence level, so if I took 100 different samples and I constructed confidence intervals for 100 different samples, so I have 100 different confidence intervals, I would expect 95 of those confidence intervals to contain the population proportion. 5 of them would not include the population proportion. So I would expect 95 of them to have that if I constructed 100 different confidence intervals based on 100 different samples. All right. So this is how we write our confidence interval. This is one of the ways. We would write our point estimate. So whatever our sample, the proportion of whatever we're looking at for a sample, then you'd say plus or minus our margin of errors. Remember in my example earlier, I said 38% of the vote plus or minus 3%. The 3% is the margin of error, and that 38% would be the proportion based on my sample. This is one of the ways that we write it. And your homework will have you write it both the two different ways, and I will make sure every example I do, I write it both ways so you can see what that looks like. And we are going to be getting a new calculator function also today. All right. It's going to be so much easier once we're doing examples. All right, so these are the 3 things that we use for our margin of error. So number 1, actually, we don't tend to use standard deviation. We will use that with when we're doing mean. We obviously won't be doing that with actually, I just lied to you. Ignore me. Ignore that. we will be using standard deviation. So we have the level of confidence. So our 95%, 99%, I'm 95% confidence. So as my level of confidence increases, my margin of error is also going to be bigger. Because if I want 99% of my confidence intervals to contain the population proportion, I'm going to need a bigger margin of error to capture that population proportion. Sample size is important because if a bigger sample size, I am more likely to capture or to be close to the population proportion. So bigger sample size, I'm more likely to be close to that population proportion. Then standard deviation. So the standard deviation that we are going to use is going to be that new standard deviation, that standard error that we calculated in the last section. The larger spread out my data is, the wider my interval is going to have to be. So bigger standard deviations are going to give us a bigger interval. Right. Give you a second to write that down. I'm going to take a drink and then we will do some examples. I believe that there's a question in your homework that asks this, like, if my sample size is bigger, what happens to my margin of error? I believe that there's a question in your homework for this, so you might want to like tab this page. I don't remember if it was on mean or if it was on proportions, but either on proportions or on mean, one of them has a question about this. Okay. This is just a reminder. When we had a sampling distribution of p hat, we had our mean. Our mean was equal to the population proportion. The mean of our sampling distribution was equal to the population proportion. Our standard deviation was this. We used this standard deviation formula. This was our new standard deviation. And remember that this right here, the NP times 1 minus P greater than or equal to 10, that indicates that we're normally distributed. This is for normal. Plus, we need to have independence when sampling. So our sample size needs to be less than 5% of our population. Okay, this is independence. These are all the things that we talked about on Thursday last week. So we still need to check these things. This is important. Okay. Okay, this is the math that we're going to be doing. So this right here, this piece right here is our standard deviation. Sorry, I lied. This piece right here is our margin of error. Sorry. I'm going to explain what the pieces are in a second. This is our margin of error. We take our p hat and we subtract the margin of error, and that gives us the lower bound of our interval. And you take your p hat and you add the margin of error. That gives you the upper bound of your margin of error. This z-score right here, notice it says z alpha divided by 2. It is based on, I'm going to draw a beautiful perfect curve here. So let's say that this is, say I'm 95%. I have I'm creating a confidence interval for 95%. That's what I'm doing. That's that is my goal here, to create a 95% confidence interval. Confidence interval is like the center 95%. So I have 2.5% down here, and I have 2.5% up here. That's what this alpha divided by 2 means. I'm going to find the z-score. I'm going to find the z-score that corresponds to 0.025 and the z-score that corresponds to 0.025. 975? 975. What am I doing? I can't math. 975. So because we are doing the center 95%, we did this, I believe, chapter 7. We have to find the z-scores that go with 0.025 and 0.975. The nice thing is that they're the same z-score, just one's positive and one's negative, and we only use the positive. So if you just find this z-score, you're going to be good. But you have to cut the alpha in half. What alpha is, let's stick with our 95% confidence interval. So I have a 95% confidence interval. What alpha is if I did 100% minus 95%, this gives me 5%. My alpha is 0.05. It's that 5%. That's what alpha is. And we talk a lot more about what alpha means in chapter 10, but just trust that alpha is that difference between the confidence level and 100%. That's what the alpha is. The difference between the confidence level and the 100%. So when we're looking for that z-score, we divide it in two. Once we're starting doing the math, it's going to be a lot easier. Okay. So you take that z-score that you find and you multiply it by the new standard deviation, and that gives you the margin of error. We're almost there. We're almost to the math. Give you a second to write it down. Okay. And look, this is the picture I basically just drew. Okay, so our z sub alpha divided by 2, it's called the critical value. That z-score we find is called a critical value. So your homework is going to ask you for the critical value. That z-score is that critical value. Because what it's telling you is that your edge of your confidence interval is this many standard deviations away from the mean. And so you just multiply that z-score times the standard deviation and it gives you those edges. You'll see in a minute. All right. So on the bottom of your z table, so that table that we've been looking at, that table that we look at, this table right here, it's just the bottom of that z table, this right here, these are the most commonly used critical values. So they did the work for you. Okay, I noticed that there's a delay. I'll wait a second here. My goodness, there's quite a delay. Hopefully that'll fix by the end of the class. Okay. They've done the math for you. They did the dividing by 2 and all of that. These are the most common ones. So if it's a 90% confidence interval, you're going to use 1.645 as your critical value. If it's 99%, 2.575. Now, if they give you a weird one, so let's say they want to be, let's say they want to be 80% confidence level. They want to do an 80% confidence level. You're going to find that difference. So the center 80%, there's going to be 10% here and 10% here. So I'm going to do 0.90 with inverse norm. And that'll give you your z-score. So if whatever they give you is different than one of these, you'll use inverse norm. Now I'm going to tell you on the test, the one I give you will be one of these. I'm not going to go off book and give you a strange one. I will absolutely on the test give you one of these ones, one of the ones at the bottom of your sheet. So no worries there. You'll absolutely get one of those. But I know my open math does weird things sometimes. Sometimes they give you a weird one. So make sure that you're cutting that alpha in half before finding your z-score. Are we good so far? I know I'm talking a lot and I haven't written much. I haven't done much math yet. Are we okay? Questions? All right, good, thank you. Moving on. So our interpretation, so we already did this. So we would say, I am, our confidence interval would say that whatever percent, 90%, let's say, that 90% of all of our sample sizes whose will result in an interval that contains the parameter, or 95% or 99%. We never have 100%, but we do go as far as 99%. And I'll be writing out what I expect your conclusion to look like. So no worries there. Are we ready? Yes, we're ready to do some math. All right. In July 2008, a Quinnipiac poll asked 1,783 registered voters whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. We want a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for people convicted of murder. So first thing, our p hat. We already did the p hat. I'm going to write the math anyway. 1123, 1783. So it was 0.63. That was our p hat. Okay, we need to check. So 1783 is definitely less than 5%. So 1783 is less than 0.05 of our population. Absolutely. So this is definitely independent. And then doing our NP 1 minus P, or NP 1 minus P greater than or equal to 10. We don't have the population proportion, so we're going to be using P hats because we don't have a population proportion. They didn't give it to us. All we have is our sample. And this is usually the case. Usually you won't have the population. So I'm going to say 1123, right? No, 1783 times 0.63 times 1 minus 0.63. I'm going to put that in my calculator. Oops. Well, 415.6. Yeah, I would say that's greater than or equal to 10. So all of those things have been met. So we're good there. So now what I'm going to look for is I'm going to look for my critical value. The critical value here at 90% is one of the ones that we have on our bottom thing here on our table. So it's 1.645. So this is telling me that the edge of my confidence interval is going to be 1.645 standard deviations away from 0.63. So now I need to calculate my standard deviation. So my sigma sub p hat is going to be my p hat, so 0.63 times 1 minus 0.63 divided by my sample size, 1783. If you are really careful with your parentheses, you can put this whole thing in your calculator at once. If you're not confident in your ability to do that, just do it piece by piece. 0.0114. If you did the math also, can you confirm my math? Okay, good. Thank you. Okay, so the way that we find our margin of error, now I'm not sure what my open math does. The PowerPoint slide, it frequently uses just a capital E. I usually do capital M, capital E. I'm not sure if they do a capital M or if they do an E or what they do, but the margin of error here, I'm just going to do ME. is going to be my z sub alpha divided by 2 times my sigma p hat. So my margin of error, 1.645 times 0.0114. This is going to give me the edge of my confidence interval. Or give me at least how far away from my my p hat it is. 0.01875. So we're about 2%, about 2% away from, and you probably could round it to 2%. And that's probably what they would do if it was like some national poll. They would probably round it to 2%. So the way that we're going to write this, so if I was going to do a conclusion here, the way that I'm going to write it, so I'm going to do p hat plus or minus my margin of error. So 0.63 plus or minus 0.01. I'm just going to go that far out. So my population proportion, so the actual number of people who are in favor of the death penalty for people convicted of murder is 63% plus or minus 2%, or plus or minus 1.9%. The other way that we can write this, we can write it as an interval. You'll be required to do it both ways in my open math. So I can actually add it. So this is the other way is lower bound, upper. You just put it in parentheses. So I would do 0.63 minus 0.019. I know I could do this in my head. 0.611, 0.63 plus 0.019. There's the other way to write it. These are the two in the green are the two different ways that we can write our intervals. Technically, I don't have room for this. I'm gonna write with pink up here. We could also write it like this, and I know that this is going to be, you could do 63% plus or minus 1.9%. I don't care which way you do, or 61.1%, comma, 64.9%. I'm not going to be mad either way. So if I was to answer this, I would say we are 90% confident that the actual proportion of voters who are in favor of the death penalty is between 0.611 and 0.649. Or you could say, I'm 90% confident that the proportion of people who are in favor of the death penalty are 0.63 plus or minus 0.019. Or if this was like some sort of a poll somewhere that they put on TV, they'd say 63% plus or minus 1.9%. Questions before I move on? Okay. The next page is them. They did all their math already. Except for, I don't know why all the math part is missing. They got the same numbers though. They rounded. They did their rounding. So this is the way that they wrote it. We are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is between 0.61 and 0.65. This is a perfectly beautiful. I know normally I say that they use too many words, but this is a perfect conclusion. This is it's perfect. If you write it like this, 100%, it's perfect. I believe that on your test, I'm going to have you type out a conclusion. So if you want to use this as an indicator, so if you want this to be like your template of what you use, is perfect. And it's in the context of the question. It's just perfect. So look, they checked all of their things here. They got their Z-score. They did all the things that we did. I don't know what happened over here. There was math there. Good thing I just wrote it out. All right. We're going to do another one, and then I'm going to show you the calculator function. So we're going to do another one by hand, and then we'll do the calculator function. So Gallup organization conducted a poll in which a simple random sample of 1,016 Americans 18 or older were asked, do you consider the amount of federal income tax you pay is fair? Of the 1,016 adult Americans surveyed, 558 said yes. So things we need. We need our p hat. I just do it up there because I don't have a ton of room. We need our p hat. So our p hat would be I'm going to do 0.55 because it's 0.549. So about 55% said that I think that number would be lower these days. I don't think that that's going to be accurate. If we did another one of those, I don't think it would be, people would say that. All right, next thing. 1,016 adults is definitely less than 5% of the population. So I'm going to do this. 1,016 is less than or equal to 0.05 of the population. It's good. We've got to be less than 5% of the population. We're good there. Now let's do our NP 1 minus P greater than or equal to 10. So 0.55, 1 minus 0.55. I forgot the N, 1,016. So let's go ahead and math that out. About 251. That is greater than or equal to 10. So this is for independence. Our samples are independent. This was for normal. We are normal. Now, you're not going to have to do that on your homework. But if you do it on your test and you get that it's not normal, it's okay. Just continue on with your math. Just make an indication that it's not greater than or equal to 10. But just keep doing the math anyway. I can't remember. I thought there was a problem somewhere, and I couldn't remember if it was the test or if it was the homework, that there was one that wasn't right, but you still just did the math anyway. I can't remember. I mean, I'm going to check the test when I write it, but I am human. I do make mistakes. All right. Critical value. 95% confident. We have a critical value right there. It's good. Now we need our standard deviation. You absolutely can put it in your calculator as 0.55 times 0.45. I just, in the past, I have written down 0.55 times 0.45, and people are like, where did the 0.45 come from? So it just makes sense to just keep it with the 1 minus. When I put it in my own calculator, I just have the math in there. I'm going to do 0.016. Is that what you got? I'll give you a second. Okay, good. All right. So remember, your margin of error is the critical value times the standard deviation. So this will get you your margin of error. So it's approximately, yes, good job. Uh-oh. So far I forgot a zero. Yay, good job. So we have about I think that probably, I'm guessing that we would just round it to 3%. Why not? 3% is a pretty number, so we're just going to round it to 3% because it makes it easier. So when you write your answer, it is p hat plus or minus your margin of error. So we do 0.55 plus or minus 0.03 or lower, comma, upper. We are 95% confident that the actual proportion of, is it just Americans, adult Americans who believe that the amount of federal income tax they pay is fair is between 0.52 and 0.58. Or you can say we're 95% confident that the actual proportion of Americans, adult Americans who believe the amount of federal tax they pay is fair is 0.55 plus or minus 0.03. Questions before we move on? No? Okay. I'm going to give you a calculator function. And it's so cool and fast and easy. There's just a couple little tiny things I want to. Okay. Our calculator function is this right here. And we're going to do this voter one, or the income tax one in a second. That is our calculator function right there. One prop z interval. One proportion z interval. We're dealing with one proportion and we're finding a interval based on z scores. That's what it stands for. One prop z interval. So let's go over to our calculator. So one way to remember which button to click on. So remember when we clicked on VARs, that was when we were dealing with distributions, normal distributions, binomial probability distributions, things like that. Now we're doing tests. We're dealing with statistics. This is not probability. Most of our probability stuff goes through the VARs button, which is for distributions. Most of our statistics goes through the stat button. This is statistics. So I'm going to go on stat, and this is a test, stat tests, and we're going to go down to one prop z interval. Do not mistake number 7 for what you want. That's not what we want. One prop z interval is right here. It's letter A. So stat, arrow over to tests, whoops, and go down to A, one prop z interval. So we're going to put in our X value here. So our X value is the number of successes. We had 558 successes. Our sample size, 1,016. Our confidence level, 95%. So make sure to put it in as a decimal like this. Nice and beautiful. And hit enter. What it gives you the interval, it gives you the lower and the upper, and it gives you the p hat. So our p hat was 0.95, and our interval was 0.52 to 0.58. This is totally right on par with what we got, which is amazing. So this is beautiful and well and good, but there's a couple of little hiccups you're going to run into that are easily fixed. Super easy to fix. Okay. Just a second here. Cancel. Okay. Couple things. I'm going to write this down what they have here, and I'm going to write down what the screen shows so that I'm just going to do 1862. I'm going to write down exactly what they have. Not all of the p hat though, because that's really long. Okay, go back to my screen. All right, so this is what we're given. So what if MyOpenMath says that they want it in this format? If MyOpenMath wants it in this format, you're going to have to take this value right here and subtract the p hat from it. That will give you your margin of error. It gives you your p hat. That's this piece right here. But you're going to have to take that upper value and subtract the p hat from it. And it gave me basically what I had. It gives me so when I do 0.57981 minus 0.54921, I get 0.0306. So it's perfect. So I would do my 0.55 plus or minus 0.03. Okay, that's perfect. The other issue that you will come across is it will give you a percent. It'll give you the population proportion or the sample proportion. It'll say, like, let's say, for example, that it said, I'm gonna delete all of this. Is it okay? I'm gonna delete it. Okay. Because I'm gonna use different numbers here. So you might get a question that said, like, let's use this question as an example. And I'm not going to use, this is not the number we're dealing with. But let's say that they sampled 1,016 adults and 56% of them said yes. But when I multiply 0.56 times 1,016, I get 568.96. I can't put a non-integer answer in my calculator. Oops. When I do that, let me see here. Stat. If I put a non-integer answer in here, I don't know what I'm doing. Okay. If I said, okay, let's do, or if I did put the math in there, let's say I decided to do 0.56 times 1016. It's going to give me an error. See, it's not an integer answer. It's going to give me an error because it has to be an integer. There's a way around this. So if I do 0.56 times 0.16, I'm just going to round this to 569. Just round it, like literally round it. It will give you the correct answer. I tested it on several of the problems in MyOpenMath. It'll give you the correct answer. So instead of using 568.96, I need to be on tests. I'm going to do 569 instead. And that will give me the correct answer. Whoa. I don't know what my problem is there. Hit that button too many times. I mean, you could do that, or you can, I mean, you could do the math by hand if you want, but rounding it like that will be fine. Because look at this. Look at my p hat. It's basically 56%, right? It's 56% because clearly when they polled people, they had an integer. They didn't poll people and have 568.96 people say yes. So common sense tells us that 569 people said yes. Questions so far? That makes sense? Okay, good. All right. This I already told you. So this right here is critical value. This is my margin of error. So this is my critical value. And this right here is the sigma sub p hat or standard error. All right. So the next thing we're going to do is we're going to look at sample sizes because frequently we want to be able to say we want to have a 95% confidence interval. You know how sure you want to be, and you know approximately what your margin of error you want. And so you can sample the correct number of people to get what you want. And it sounds like you're being shady, but it's really not. As long as you poll enough people, you're good. Let me show you how we do this. Okay. So all I did was take my formula, take this formula right here, and I algebraed it out. I just did some algebra to solve for n. That's all I did, was took that algebra and solved for n. When I did that, I got this formula right here. I'm going to let you write it down. This will give us the sample size. There's an issue with this, but I will help you to figure it out in a second. So this is basically our formula. So you take p times 1 minus p and multiply it by the critical value divided by the margin of error squared. Our issue is, in order to find p hat, we need to have a sample size, because p hat is our number of successes divided by the sample size. So there's a couple of different ways to get around this. Actually, I mean, there's one way, but never mind. A couple of different ways we can get around this. And I want to show you that in a second. So one way to get around it, you may find a study performed earlier, or maybe somebody did a pilot study and we're just redoing the study. Maybe they didn't like their margin of error. Maybe it was too big of a margin of error or something, and so they want to do another study. Or maybe somebody did a study 3 or 4 years ago, and so that gives us kind of a ballpark of where our proportion is. So you could use that for your p hat if you need to. If there was no other study, we need to use a p hat that'll give us that largest possible value. So the one that is, like, if we use 0.5, it's going to give us the largest possible value. That way we're not underestimating. So if we don't have a pilot study, use 0.5 for your p hat. And I want to point out 0.5 times 0.5 equals 0.25, because this would be p hat and this would be 1 minus p hat. So in the formula for this, you're going to see them just use 0.25. I don't care which way you do it. If you write them out like this, or if you write 0.25, it's the same thing. Okay. So here's our formula, as we said. Now, the important thing here, when you are finding the sample size, you always round up to the next higher integer. Even if my answer was 125.01, we would round to 126. So if you have a decimal, we always round up. The reasoning behind this is, if I had my answer, my sample size showed 125.1, 125 is too small, because it has to be at least 125.1. 125 is too small. We always round up. I compare it to a bus. So let's say that we have a whole bunch of students in the bus. And let's say that we can fit 50 students in each bus, not a single one more. 50 is the maximum capacity. If I have 205 students, I have to have that fifth bus. I can't just have 4 buses. I have to have that fifth bus. It's the same thing here. You've got to round up to the next integer. Okay, let's do some math. This is what we already talked about. 0.5 times 0.5 is 0.25. Okay. A sociologist wanted to determine the percentage of residents of America that only speak English at home. We want to know the sample size that should be obtained if she wishes her estimate to be within 3 percentage points. This is my margin of error with a 95% confidence level. That's my confidence level. In the year 2000, there was a a survey done, and there was 82.4% was the answer there. So that's what we're going to use. So remember our formula, n equals p hat 1 minus p hat, my z-score over my margin of error squared. Okay. 90% confidence interval. You're going to start having these memorized. Pop over here. 90%, 1.645. So my z, there's a delay again, darn it, 1.645. My margin of error, 0.03, and my p hat, 0.824. So these are the numbers that we're using. If you're careful with your parentheses, you can put this whole thing in your calculator. So I have an N 401.42. I have to round up. Did I put it in my calculator wrong? 0.8. Oh yeah, I put it in my calculator wrong. You did too? It happens. Okay, I put it in my calculator wrong. I put 845 instead of 842 or 82. I put 845 and 842. I didn't even do 824. What is my problem, man? Okay, there we go. You're right. You were right. I was wrong. So n equals, I got 436.04. See, I'm so glad you type it in the chat because somebody's got to check up on me. So we're going to use 437. We always round up. So we will need 437 in our sample size in order to get the margin of error of 3 and the 90% confidence interval. So we would then we would turn around and we would do our study. We would survey 437 people, and then we'd have a new p hat. So because you would use the new p hat now for your study or whatever, because it's probably not going to be exactly 82.4%. Thank you. Thank you for showing me the error of my ways. Right, questions. We're going to do another one. Okay. This is the same math that we just did. I'm going to have you try this one on your own. I'll write down the formula. And an economist wants to know if the proportion of U.S. population who commutes to work via carpooling is on the rise. We want to know what sample size we need. 2 percentage points is our margin of error, and we're using a 90% confidence. There was an estimate in 2009 that was 10%. You thought you forgot to square? We're squaring the whole thing, though. You square both the whole. You do the z divided by the margin of error and then square that. Okay. I'm going to write down the formula again. So n equals p hat 1 minus p hat z alpha divided by 2 over e squared. My p hat it's 90%. Yeah, 1.645. Or your z alpha divided by 2, 1.645. Okay, I will work quietly behind you, but go ahead and see if you can get this. That's what I got. Don't forget the rounding up. Good job. So they would need to take a sample of 609 people in order to get that margin of error with the 90% confidence interval. So what if the economist didn't use a prior estimate? So what if they didn't find a prior estimate or they didn't like the prior estimate and they decided not to use that? So remember, if that's the case, then we use this 0.5 times 0.5 z sub alpha divided by 2 over e squared, or you can do it like this. So let's go ahead and calculate that sample size. I will work quietly behind you. Yeah, isn't that incredible, the difference? So, moral of this story, if you can find a prior estimate, use one. Otherwise, you're going to have to poll 1,000 more people, more than 1,000 more people. It's always significantly higher. It's always so much higher. So if you can find a prior estimate, use it. Usually, you can Google something and get a prior estimate. Now, if you decided that you wanted to use a confidence interval on your final projects, which I've been teaching this class for, I think I've been teaching this class for like 5 years, 4 or 5 years. I've had two people do confidence intervals, and you definitely don't have to. But if you chose to, um, we're just going to call your sample size good, and you're going to create your own margin of error. And you could always, if you wanted to, you could always say, if I wanted to keep my margin of error within this, I would use this sample size instead. But for this paper, I'm doing this. You don't have to do confidence intervals. I'm just saying if you chose to. So it's, most people don't even use the things from chapter 9 and chapter 10 in their final projects. Most people stop much earlier than that. However, we've had some really good hypothesis testing in final projects before, which that's chapter 10. So, just consider things. I don't want you doing math just for the sake of doing math, but if you can see how it could be meaningful in any way, then why not? You can throw it in there. All right, that was the last slide of information that we have. I told you it was going to be just about an hour, and look, it is 6:01, so it's exactly an hour later. So that is the last information I have. If you have anyone have any questions while are being recorded? All right, I'm going to turn off the recording then.